Imagine a world where computers are no longer bound by the limits of classical physics. What possibilities might that world hold? In the beginning, our ancestors counted on their fingers, marked notches on bones, and moved pebbles around in the sand. They created the abacus, a simple device that allowed for quick calculations, using beads slid along rods. This was the dawn of computing, a time when the human brain was the most powerful processor in existence. Then came the 19th century, a period of great mechanical innovation. Charles Babbage, an English mathematician and inventor, envisioned the first mechanical computer. He called it the analytical engine, a machine far ahead of its time that could perform any mathematical operation. It was a marvel, yet it was limited. It could only hold one operation at a time and couldn't store data. These limitations were the catalyst for the next leap in computing. As the Industrial Revolution powered on, so did the need for more advanced computational devices. The punch card system was created, allowing for more complex operations and data storage, but even this was not enough. As we moved into the 20th century, our understanding of the physical world expanded. We discovered the electron, the building block of electricity, and soon after, the first electronic computers were born. These machines were a revolution, capable of performing calculations at speeds unimaginable to Babbage and his contemporaries. But they were still limited. These machines were enormous, consuming whole rooms and requiring vast amounts of energy. And they were still bound by the laws of classical physics, unable to perform multiple operations simultaneously or hold vast amounts of data. Yet these limitations only served to drive innovation further. As we delved deeper into the mysteries of the universe, we discovered quantum mechanics, a realm where the rules of classical physics no longer apply. This was the beginning of a new era, an era where computers could perform multiple operations at once, hold virtually unlimited amounts of data, and operate at speeds previously thought impossible. As our understanding of the physical world expanded, so did the capabilities of our computing machines. The invention of the transistor marked the beginning of the electronic revolution in computing, a statement of profound truth. When Bell Labs announced the invention of the transistor in 1947, it was the dawn of a new era. The transistor, a tiny device capable of amplifying or switching electronic signals, became the fundamental building block of modern electronic devices. The integrated circuit, or the microchip, soon followed, packing thousands of transistors into a space no larger than a fingernail. This was a technological leap that truly brought the power of computing into the hands of the many, rather than the few. Imagine for a moment the world before this electronic revolution, a world in which computers filled entire rooms, consumed enormous amounts of power, and could only be operated by a select group of trained professionals. The invention of the transistor and the integrated circuit changed all of this, making computers more compact, more efficient, and most importantly, more accessible. It was these technologies that gave birth to the personal computer in the 1970s. The notion of a computer in every home, once a far-fetched dream, became a reality, and with it, the way we live, work, and play was forever changed. The electronic revolution didn't stop there. It also paved the way for the invention of the internet. The internet, a vast network of interconnected computers, transformed our world into a global village. It has revolutionized the way we communicate, the way we learn, the way we do business. The transistor and the integrated circuit were truly revolutionary. They turned computers from colossal, inaccessible machines into indispensable tools of modern life. They ushered in an era of rapid technological advancement, the effects of which we are still feeling today. But while we marvel at the power of these machines, it's important to remember that they were just the beginning. As powerful as these machines were, scientists were already dreaming of a new kind of computer, a dream that would lead us to the frontier of quantum computing. And that, my friends, is where our story takes its next fascinating turn. Enter the world of quantum computing, where the rules of classical physics no longer apply. In the realm of quantum computing, we're not just dealing with ones and zeros anymore. We're entering a domain where bits of information known as qubits or quantum bits can exist in multiple states at once. This is due to a quantum phenomenon known as superposition. Imagine a coin spinning in mid-air. It's not just heads or tails, but both at the same time. Similarly, a qubit can be both 1 and 0 concurrently, opening up a whole new world of computational possibilities. Now let's dive a little deeper. Quantum computing also exploits another quantum peculiarity known as entanglement. Entanglement is a kind of super relationship that can exist between quantum particles. When particles are entangled, the state of one particle is directly related to the state of the other, no matter the distance between them. This spooky action at a distance, as Einstein once called it, allows quantum computers to process a vast number of computations simultaneously. So, what's the big deal about quantum computing? Why all this excitement? Well, imagine being able to solve problems that would take a classical computer longer than the age of the universe to crack. Quantum computers have the potential to revolutionize many fields. For instance, they could solve complex mathematical problems, break almost all cryptographic codes, simulate the behavior of matter down to the atomic level, and optimize complex systems such as global shipping networks. But it's not all smooth sailing. Quantum computing also presents its own set of challenges. For one, maintaining the delicate state of qubits for long periods is a major hurdle. Moreover, quantum computers are highly sensitive to environmental changes and require extreme conditions to function. Quantum computing promises to revolutionize everything from cryptography to drug discovery, but it also presents new challenges. As we forge ahead into the quantum era, we must navigate these challenges and explore the untapped potential of this groundbreaking technology. Quantum computing is not without its challenges. From maintaining quantum states to error correction, the road to practical quantum computing is fraught with obstacles. Let's delve into the intricate world of quantum complexities. One of the most significant hurdles is maintaining the delicate state of qubits, the fundamental units of quantum information. Unlike classical bits that are either 0 or 1, qubits can exist in multiple states at once, thanks to a property called superposition. But this extraordinary state is extremely fragile, disrupted by the slightest changes in temperature or electromagnetic radiation. This is where the concept of quantum coherence comes in. Scientists are working tirelessly to lengthen the coherence time and improve the stability of qubits. Next up is quantum entanglement, another core principle of quantum computing. This phenomenon allows particles to be linked and instantaneously affect each other regardless of the distance between them. However, creating and maintaining this entanglement is a challenge in itself, especially when dealing with large numbers of qubits. Then there's the issue of quantum error correction. Quantum computing is prone to errors due to the inherent instability of qubits. To combat this, researchers are developing error correction codes that can detect and correct these errors without disturbing the qubit's delicate state. Another challenge is scalability. Quantum computers of today can only handle a small number of qubits. To be practically useful, we need to scale up these systems to handle thousands, even millions of qubits. This is a monumental task that requires significant advancements in technology and design. Finally, the quantum programming languages and algorithms are still in their infancy. We need to develop new programming paradigms and algorithms that can harness the true power of quantum computing. Despite the daunting obstacles, the scientific community is not deterred. They are tackling these challenges head-on, driven by the immense potential that quantum computing holds. The road may be rocky, but the destination is worth the journey. Despite these challenges, the potential benefits of quantum computing are too great to ignore. So what does the future hold for quantum computing? In the realm of quantum computing, the future is nothing short of electrifying. The potential applications are vast and far-reaching, with the power to revolutionize industries and fields of research. Firstly, let's consider cryptography. As it stands, our digital security relies heavily on complex algorithms. However, in the quantum world, these could be cracked in mere seconds, rendering our current security measures obsolete. But fear not, for quantum computing also offers the solution. Quantum cryptography promises ultra-secure communication with the ability to detect eavesdroppers instantly. Next, we move to the field of drug discovery. The process of discovering new drugs, which currently takes years and billions of dollars, could be dramatically accelerated with quantum computing. By simulating how molecules interact, quantum computers could help scientists design new drugs and understand diseases at an unprecedented level. Now, let's not forget about climate modeling. Our current models are good, but they're not perfect. Quantum computers, with their extraordinary processing power, could help us create more accurate models, predicting weather patterns and climate changes with greater precision. In the realm of artificial intelligence, quantum computing could lead to significant advancements. With the ability to process vast amounts of data at lightning speed, quantum computers could potentially supercharge machine learning algorithms, leading to more intelligent and efficient AI systems. And these are just the tip of the quantum iceberg. Other sectors like logistics, finance, energy, and even space exploration stand to benefit from the quantum revolution. Quantum computing is not just about faster processing, it's about redefining what is possible. It's about unlocking a new level of complexity and understanding in our world. It's about transforming how we solve problems, how we innovate, and how we progress. So, as we stand on the brink of this new era, it's clear that our future is intertwined with the quantum world. The impact of quantum computing will be profound, reshaping our society and the way we live. The future of computing is quantum, and that future is closer than you might think. As we stand on the brink of the quantum revolution, we find ourselves asking, is quantum computing the next revolution? It's a question that echoes through the corridors of our collective consciousness as we grapple with the potential of this futuristic technology. In our journey through the captivating world of computing, we first encountered the dawn of this technological era, a time when the concept of a computer was as nascent as the morning sun. We then leapt forward to the electronic revolution, a period that saw an explosion of innovation as transistors replaced vacuum tubes, bringing with them the promise of smaller, faster, and more efficient machines. This led us to the quantum leap, the point where we began to explore the possibility of harnessing the strange, counterintuitive principles of quantum mechanics to process information in ways that classical computers could never dream of. Quantum computers, with their qubits and superpositions, promise speeds and processing power that could make our current computers look like abacuses.